Dear students, welcome back to our discussion. In the last class, we represented our VCRS, vapor compression refrigeration systems, in different conditions for refrigerant in pH diagram and TS diagrams. Now let us move on to some other discussion where we will be modifying our standard VCRS, or why we are going to modify our standard VCRS in order to improve its COP. So now let us try to improve the coefficient of performance of this VCR of this standard VCRs by implementing some minor modification. One such minor modification is called as subcooling or undercooling. Okay, so subcooling or undercooling means cooling down a particular matter, for example the working fluid refrigerant, below its normal conditions. Okay, so subcooling or undercooling means we are further cooling down the refrigerant below its normal conditions. Okay, so here how we are going to implement this subcooling. So here we are going to discuss a method for subcooling of this liquid refrigerant using cooling water circuit. So here we are going to subcool the liquid refrigerant using a cooling water circuit. So now let us try to discuss that. So here this is our VCRS or vapor compression refrigeration system. We are having the evaporator 421. We are a constant pressure heat absorption will be taking place by the refrigerant. The refrigerant will be absorbing heat from this evaporator and getting vaporized, and this vapor form of this refrigerant, it will be admitted to the inside of the compressor, where this compressor will be compressing the working fluid, that is our refrigerant, in isentropic compression process. So after this isentropic compression process, the refrigerant will be normally in its superheated vapor form. Okay, so it is this superheated vapor form of this refrigerant which is going to enter the condenser. So what is meant by a condenser? Condenser is simply a heat exchanger unit, where this high heat of this refrigerant which is coming out of this compressor, it will be rejected to some cooling medium. So here we are considering a cooling water circuit. Okay, so there will be a cooling water circuit. So a cooling water source will be there. There will be a circulating pump, a normal hydraulic pump, which will be regulating the supply of this cooling water. It is to this cooling water, this high heat or the high temperature superheated vapor form of the refrigerant, it will be rejecting the heat to this cooling water at this condenser. Okay, so after rejecting the heat to the cooling water inside the condenser, what will happen? So it is the superheated vapor form of the refrigerant which is rejecting the heat to the cooling water circuit in the condenser. So what will happen to that superheated vapor form of the liquid? It will be condensing, or the vapor form of the refrigerant will condense back to liquid form. Okay, but even though the vapor form is getting condensed into the liquid form, the liquid form of the refrigerant which is coming out of the condenser, it will be still having a somewhat high temperature. Okay, it will be still at a high pressure, that is understood, but even after rejecting the heat or even after undergoing condensation inside the condenser, the liquid refrigerant which is moving out of the condenser, it will be still having a high temperature, or it will be having still more amount of high heat associated with this. So it is this heat. Suppose we can arrange another or additional heat exchanger immediately after this condenser. So immediately after this condenser, in the normal case or in the standard VCRs, the refrigerant should have passed through the expansion valve and then later on pass on to the evaporator. But in between this expansion valve and the condenser, we are keeping an additional heat exchanger called as subcooler. Okay, so it is this subcooler or this subcooler is nothing but a heat exchanger which will be dealing with this high temperature liquid refrigerant coming out of this condenser, and this high temperature liquid refrigerant, when it is again passed through this additional heat exchanger, here also this additional heat exchanger or this subcooler, here the cooling medium will be the same cooling water circuit which is supplied by the pump, which is pumped by or circulated by a circulating pump from a cooling water source. Okay, so this cooling water will be admitted inside the subcooler, and this cooling water circuit will be taking away the heat from this high temperature liquid refrigerant which is coming out of this condenser. Okay, so when this subcooler is a additional fitting compared to our standard VCRs, so that is why a intermediate step, that is 3' is coming here. Normally after 2, the 2 means the inlet of the condenser, and in the standard VCRs 0.3 will be the outlet of the condenser, but between the inlet of the expansion valve and condenser, we are keeping an additional subcooler here. So that is why an additional portion is happening here, and that is marked here as 0.3'. So from 2 to 3', what is happening? The superheated vapor form of this refrigerant is getting condensed to a high temperature liquid form of the refrigerant. Okay, so at 0.3', the state of the refrigerant is in liquid state, but it will be at a very high temperature. So it is this high temperature liquid refrigerant at 3' which is going to enter the subcooler and rejecting the heat further to the cooling water circuit. Okay, this cooling water circuit will be taking away heat from this high temperature liquid refrigerant at the subcooler, and again turning that liquid refrigerant into still lower temperature liquid form. Okay, so the liquid refrigerant which came out of this condenser at 3', it was at a higher temperature. Okay, so after passing through this additional subcooler, that high temperature will be again further reduced to a lower temperature. So when the refrigerant is further reaching the 0.3, or before it enters the expansion valve, its temperature would have been still more lowered, or its temperature will be still lower than its temperature. What was its temperature at 3'? So it is this very low temperature or subcooled. Actually, that term is called subcooled. The very low temperature refrigerant, or the subcooled refrigerant, that is subcooled liquid refrigerant, which is going to enter the expansion valve and undergoing the isenthalpic expansion process, and finally entering the evaporator, and the cycle will be continued. So how we can represent such a case? So the subcooler is a heat exchanger where heat rejection occurs at the same pressure of the condenser. So here that is also a point to be noted. Here, even though we are fitting a subcooler over here, there is no pressure reduction happening over here. The pressure reduction is happening only at the expansion valve. The subcooler is also working at the same pressure as that of the condenser. Okay. Now, how we can represent this subcooling of this liquid refrigerant using cooling water circuit in a TS diagram and PS diagram? So everything else is remaining same. So 0.1 means 1 to 2 will be our isentropic compression process, that is represented in a vertical line in the TS diagram and an inclined line in our PH diagram. Okay, and also followed by constant pressure heat rejection. So 2 to 2', it will be the saturated vapor form of the refrigerant is slowly converted to saturated vapor form. Then again it will be converted to saturated liquid. That is at 3'. But what is happening at 3'? At 3', the liquid refrigerant which is coming out of the condenser, it is going to enter an additional heat exchanger where it will be again losing out its heat to the cooling water circuit, which means its temperature will be further reduced. But there is no pressure reduction happening at the subcooler. So this 2, 3', 3, all this will be happening in constant pressure. Once again, 2, the process 2, 3 dash and 3. This much step will be that is both the condenser step and the subcooler step will be happening at the same pressure. So we are continuing with the same pressure line over here. We are again going to decrease the temperature, which means decrease in the enthalpy. So 3 dash will be again extended to 3. Okay, so the same case applies over in the is applied in the TS diagram. 2 dash 3 dash was our normal constant pressure line. Again we are not stopping with that point 3 dash. It is further the liquid refrigerant is again passed on to the subcooler. Again a constant pressure heat rejection process will be happening. As a result, the temperature of the liquid refrigerant will be further reduced compared to 3 dash. So temperature at 3 will be at a lower value compared to temperature at 3 dash. So 2 dash 3 or the line 2 dash 3 dash 3, it is a constant pressure line, then followed by the constant enthalpy expansion process 3 to 4, and follow the constant enthalpy expansion process. It is a vertical line in our pH diagram, followed by our constant pressure heat absorption or refrigeration step 4 to 1. So here it is the 4 to 1 process, refrigeration process in our pH diagram. So what is the specialty of this method? Why we are discussing this method? If you have observed here, the refrigeration effect is nothing but 4 to 1 process, or in pH diagram H1 minus H4. So this value will be improved by using this method. The efficiency or the COP will be improved. Why? Because the refrigeration effect 4 to 1 is of a greater value compared to our normal case. Normal case means in comparison with our standard VCRS. So compared to our standard VCRS, the H1 minus H4 value or the refrigeration effect here, it will be at a higher value compared to our standard VCRS. So by simply implementing an additional subcooler over here, by simply implementing an additional subcooler between the condenser part and the expansion valve part, that is by implementing a simple subcooler, we have increased the refrigeration effect. We have increased the refrigeration effect 4 to 1 here in comparison with the standard VCRS. So this is one method to improve the COP of our standard VCRS, and this method is called as subcooling or undercooling. Here we are focusing on subcooling of this liquid refrigerant using the cooling water circuit. So thank you, all of you draw this diagram and the TS diagram and pH diagram and study. Okay.